Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to discuss the autoionization of water. Now I know that's a bit of a mouthful, but since we are working in aqueous solution, it's really important to understand the nature of our solvent. So let's see what's actually going on with water. The autoionization of water is simply how water interacts with itself, hence the autoionization of water. Let's take a look at the reaction that occurs. Here's my reaction. You can see I have two water molecules on the reactant side. Now, let's use the skills that we gained when finding conjugate acid-base pairs, and let's assign acid-base conjugate acid-base. So I'm going to assign this water molecule the role of the acid. Now, as an acid, that means it is going to donate a proton. Once it loses that proton, then it becomes hydroxide. So here is its conjugate base. So far, we have one acid conjugate base pair. Let's find the other pair. This water molecule is going to be accepting the proton off of our acid, so therefore it is acting as a base. Once it has accepted that proton, it becomes the hydronium ion. Here is our conjugate acid. This is our second conjugate acid-base pair. Remember when we were talking about conjugates, we specified that the weaker the acid or base, the stronger the conjugate. Well, obviously water is neither a strong acid nor a strong base, so that means its conjugates are very strong. Actually, this brings us back to the leveling effect. So the conjugate acid for water, the hydronium ion, is the strongest acid that exists in aqueous solutions. The converse is also true. The conjugate base, the hydroxide ion, is the strongest base that exists in water. So our common strong acids in aqueous solution are actually all stronger than the hydronium ion. Therefore, they're all classified the same. You can also have bases that are stronger than the hydroxide ion. Now, these tend to be Lewis bases because our common strong bases are producing hydroxide ions. So when we want to tease out the relative strengths of our strong acids or strong bases, we need to switch to a different solvent that gives us a larger discrimination window. Again, we did touch on this when we talked about acid and base strengths. Another thing I want you to notice about the autoionization of water is that water is acting as both an acid and a base. This means it is an amphoteric molecule. Basically, that's just a fancy word for any species that can act as an acid or a base. So water can either donate a proton or it can accept a proton. And of course, water is not the only amphoteric molecule. Another one is dihydrogen phosphate. We can see in this first reaction, dihydrogen phosphate is acting as a base. It is accepting a proton from water to become phosphoric acid, its conjugate acid. Water is acting as the acid. Therefore, hydroxide, of course, is its conjugate base. If we take a look at this reaction, you can see dihydrogen phosphate is acting as an acid. It is donating a proton. Now, once it has donated that proton, here is hydrogen phosphate as its conjugate base. And of course, in our second reaction, water is acting as our base. And we have the hydronium ion acting as the conjugate acid. Since we are talking about our solvent, I do want to talk briefly about hydronium ion versus the proton. Now, when we are in aqueous solutions, we actually never see the species H+. That proton is always going to be either attached to a water molecule or another molecule. Now, we tend to use the protons or the H plus to simplify chemical equations. So take a look at these equations right here. This is actually the same equation, but in the top equation we kept it very simple and we did not introduce a water molecule. A more accurate reaction is the second one shown here, where I have hydrochloric acid reacting with our water molecule to show hydronium, not just H+. So if we were to dig a little deeper, we would have our water molecule reacting with our hydrochloric acid. What happens is the oxygen actually pulls the proton from hydrochloric acid, and the electrons in this bond between the hydrogen and chlorine go to the chloride ion. So what we get is the hydronium ion and the chloride anion. Notice in this reaction, there is never just an H plus alone. It is always bonded to either the chloride anion or the water molecule. So when writing chemical equations, if you're ever using the proton or the H plus cation, just always keep in mind that if you're in an aqueous solution, that species actually does not exist. We just use it as a simplification. I hope this video gives you an appreciation for the complexity of water. We usually don't think about what's going on when we pour ourselves a glass, but now you can really know what's going on in that glass of water. Now, we're not quite finished with water yet, because in my next video, we are going to define Ka, Kb, and Kw. So I hope you'll join me for that. Thanks so much for watching.